So, staying with the carbon theme, this figure shows you the rising CO2 levels in the atmosphere for the last 50 or 60 years due to the release of fossil fuel carbon. Simple extrapolation of this graph, as you see here, suggests that we'll cross this boundary of 450 parts per million in the atmosphere in something like 20 or 30 years, leading to catastrophic climate change beyond 2 degrees centigrade. Rising CO2 doesn't just cause climate change, it also causes the oceans to become more acid, damaging the environment for ecosystems that form the base of many of our food chains, and particularly damaging for calcifiers such as the coccoliths that you see in this picture of the coast of the UK. We know, of course, what we should do about rising CO2 levels. What we need to do is use less energy, and to get the energy that we do use from sources that don't release carbon. This very clearly is our plan A for how we should be dealing with climate change. But so far, Plan A doesn't really seem to be working very well. You can see that if you look at a graph of the emissions for the last 12 years or so, as shown here. Carbon from fossil fuels has increased year on year, a brief blip down during global recession in 2009, but back to record-breaking levels of more than 8.5 billion tonnes of carbon in 2010. Against this backdrop, it may be wise to have a Plan B for how we deal with climate change. One Plan B is to shield the planet from solar radiation, mimicking the natural processes of volcanic particle production, or clouds, that you see on this image. If we increase the levels of particulate in the atmosphere, we may be able to manage the solar radiation, and if we do just the right level of that, we may be able to flatten off climate, as shown in this schematic. But if we do that, ocean pH continues to fall, CO2 also continues to rise, and we find ourselves locked into the need to continue to pump out aerosols. If we stop, we jump up in a very dramatic climate increase. Such solar radiation management also does not neatly correct the effects of global warming. If you look at this modelling result from Oxford of temperature and rainfall, and you look on the dashed lines what happens to China and India over 60 years of warming, those are not neatly reversed by solar radiation management, shown by the solid lines on here. Clearly there's a regional imprint and the potential for geopolitical conflict as a consequence of solar radiation management. A better solution to geoengineering, therefore, is to tackle the problem at source by sucking the CO2 back out of the atmosphere. This would level off temperature and ocean pH, as shown on here. There are at least 3 ways that we might try and do this, each one of which mimics a natural process but tries to exaggerate or accelerate it. The first is to accelerate the rate of photosynthetic removal of carbon by adding iron to the ocean. The bright colours in the North Pacific here show you where there's lots of life, because lots of iron. In the middle of the ocean there's much less life, except for in this red circle, where a ship is dumping iron out of its back and causing this bloom of life that you see. Now clearly we don't want to do that and mess with our ecosystems until we have a much better understanding of the ocean iron cycle, where iron comes from, where it goes to, and how it interacts with ecosystems. That's something we're very actively trying to work on and understand within our institute. The second form of carbon dioxide removal is to lime the oceans, to neutralise the acidity of CO2 by adding an alkali and to make this stable bicarbonate form. This is a little bit like giving the ocean a giant Alka-Seltzer. It's something that we already do, in fact, in acid lakes, and if we did it globally, it might draw out carbon dioxide from the atmosphere for us. Even applied locally, this could be very beneficial. By neutralising acidity in small areas, we might return to a more pristine environment, areas particularly at danger of ocean acidification, such as the reef environments shown here. The third form of carbon dioxide removal is perhaps the holy grail of geoengineering. And this is the idea that we might take silicate rocks, such as the basalts that you see here, and accelerate their natural weathering to form limestone and quartz, effectively building materials. This is something that we've just hired a new fellow in our institute to work actively on. I don't want to leave you, though, however, with the idea that we should be pursuing geoengineering or planning to pursue it. What I want to say instead is that we should be researching the potential and the risks of such geoengineering. We need to look at the chemistry, environmental science, the engineering, law, governance and ethics of geoengineering, and that's just the sort of enterprise that works well in an establishment like the Oxford Martin School. One thing that's definitely true about geoengineering, though, and we don't need research to know, is that any sort of geoengineering solution will have to be done on the same sort of scale as the current global energy industry. It'll be big, it'll be ugly, and it'll be expensive. but it may still be better than the sort of catastrophic climate change that we will see if we don't curtail our carbon emissions. Thank you.